Dear all, thanks first to all of you for joining and welcome to today's webinar on hydrogen, how hydrogen can claim its place as a clean source of energy for sustainable mobility. I'm Virginie Toussaint. I will act as the moderator for today's session. So in today's webinar, we will share with you our point of view together, Capgemini Engineering with Air Liquide, to learn more about the usage of hydrogen in transportation markets. This is also a unique opportunity to understand what are the challenges that the transport segment needs to tackle, how managing the costs for adapting existing and developing new vehicles and infrastructure to integrate H2 as an energy source, and how disposing H2 at the right place, time, and purity level. Today, our speakers are Mr. Jean-Luc Chabaudy, Director Research and Innovation at Capgemini Engineering. And I'm very pleased as well to welcome Mr. Pierre Crespi, Innovation Director at Air Liquide. Just before we begin, I would like to cover a few important points. If you have any questions during the webinar, you can send your question in the Q&A console and submit them for our speakers. At the end of the webinar, we will ask you for your feedback and we will take only a few minutes and it will be extremely helpful. So the webinar recording and presentation will be made available on our website. With that, I invite, first of all, Jean-Luc Chabaudy from Capgemini Engineering to start the session. Jean-Luc, the floor is yours.
I'm very proud to be absolutely frank on this, having this opportunity to share our vision and jointly with Air Liquide and Pierre Crespi. So the agenda of today is, let's start by some basics and some facts and figures, just to, I think that most of you knows the basics that I will share, but I think it's important because I'll come back later on my presentations. So hydrogen, this is not toxic. First, it dilutes very, very rapidly into the air, more rapidly than air into air, but at a very, very low level of concentration, around 4%, it can explode. It leaks very easily due to its very low viscosity, and it's extremely flammable at very low inflammatory energy, 10 times less than natural gas. But this is something which is very interesting. We'll come back a little bit later on. It's also corrosive for metals and some alloys. So we'll see on the next slide that it has a very interesting ratio, energy versus weight, but not that good when talking about energy versus volume. And just to illustrate, 1 liter of kerosene equals 3,000 liters of hydrogen at gas form, and equals to 4 liters of liquid hydrogen stored at and maintained at minus 253 degrees. When talking about the production of hydrogen, I think everybody knows this kind of rainbow, lots of colors, just to discriminate and present different ways to build and produce hydrogen. Let's focus on the three main colors. First one is gray. It's made of vapor forming of water. It's the way the hydrogen is currently produced and produced for decades. So it's a process that the industry controls very, very well. It has only one issue, one problem. It generates a lot of CO2 into the atmosphere. Solution might be the blue hydrogen, which is gray, but the CO2 which is generated during the production is not released. It's captured and stored and to be used for further industrial applications, but also combined with hydrogen to produce synthetic fuels. But the most interesting color is the green H2, made of water electrolysis that requests some electricity, and the green color is obtained when this electricity comes from renewable energy, mainly solar panels or wind farms, and eventually hydraulics. Some very precise numbers to compare hydrogen with some hydrocarbons and notably methane. So as we said before, this is the strongest hydrogen in terms of ratio calorific value per mass unit. It has a very interesting low density, but the ratio calorific versus volume is not that good compared to the classical kerosene and other carburants. So hydrogen is also very interesting because As said before, it can be burned onto engines, and notably for the aviation, but not only. But it also can generate electricity, like a kind of a battery. So this is a very effective and very interesting way and mean to store electricity. Out of that, you just have capacitors and some devices, but not that efficient and notably not capable to store a huge amount of electricity. So the technology, I think everybody knows that, is called the fuel cell. Okay, it's a kind of chemical engine, and there are different technologies of fuel cell. The most common in our world, in the world of mobility, is the proton exchange membrane, PEM, which is very interesting for any mobile application. But everything has always some kind of dark side, I'd say. Here we have huge sensibility to CO and humidity and other factors. And this is very important to understand that, basically speaking, the current technologies on fuel cell leads to an effectiveness of around 60%. Okay, but when you add all the components around the fuel cell, the piping, the compressor, the heat exchanger, and all the components which are in the converter and so on, the effectiveness can drop down very easily. So it's a real engineering challenge to maintain and to control the effectiveness of the fuel cell. Another important notion to consider, I think everybody knows that the fuel cell is never within a vehicle used by itself. You always have a battery, different kind of architecture. Sometimes the fuel cell is the primary source, sometimes the battery is the primary source, but you always have a combination of the two, and in some other vehicles, some other energy sources. So it's a key engineering challenge to control the hybridization of all those kind of energies. I won't go into details for the cost. I will leave Pierre. Yeah, I think he has interesting information to share with us. But just to share the situation in 2017 when comparing the biomethane, the green hydrogen and the gray hydrogen. And there we can see that the biomethane is more expensive, just followed by the green hydrogen and the gray. Interesting to note that the objective in 2030, first of all, is to decrease all the cost. Okay, but having the green hydrogen cheaper than the gray. And if we go to 2050, there we can see a huge drop in the price of the green hydrogen, which is a very important challenge and one of the biggest challenge if we really want to have hydrogen for the mobility. And I think Pierre will come back on this afterwards. So it's the long story. And not only when considering the latest 15 years, so it's a graph that shows investment on the main blocks around the world: China, Europe, Japan, United States, so on. So quite interesting to see that 15 years ago, the United States were investing quite a lot on hydrogen, probably for industrial applications. But after that, that decreased. I think that things are coming back and happening back in Houston. So I think the United States is coming back in the loop. So we can see Europe is having a strong position on that, and China is coming. So I don't want to go to science fiction, but if we consider the solar farm battle, China versus the rest of the world, if we consider the battery battle, and if we consider all the efforts which are putting onto the table by the Europe and all the countries to build a battery gigafactory in Europe, we can imagine that this is the same kind of battlefield that's coming up, that's going on regarding hydrogen. As a result, because of, or thanks to the fact that the society and all the industries are now sensitive on global warming and CO2 contribution, there is a fight, a worldwide fight against CO2 emission. Okay, so as a result, lots of countries having now H2 roadmaps, lots of projects all around the world. The key places around the world where things are happening: Europe, Asia, and Australia, and there are lots of money on the table. And we'll see that when looking at what Europe is trying to build, a strong vision and clear plans, very detailed plan on all the applications that can use hydrogen to reduce the CO2 emission and global warming without decreasing the performance. So hydrogen supply, I won't let me I'll put my pointer. That will be, give me 1 second. Yep. So here, the power supply, I won't go into details. This is the cost of the question of the price, but I think Pierre will come back in details on that. What you can note here is as part of the distribution dimension, we have nowadays pipelines that are sharing hydrogen. Pipeline will continue, probably more dedicated for the industrial applications, while for lots of mobility applications, production will be local. But I think Pierre will give us some information on that. So what's new? Europe built a kind of global vision, 3 pillars to address: the production, the distribution, and the end usages. And out of that, it builds a very detailed plan. And we are now focused on these parts. But again, the Europe put everything on the table, again, to identify any way, any mean, any need, where any opportunity where hydrogen can bring the value we are expecting for. Here we can see also this notion of H2 valleys, coming back to what I said for the transportations. And there are lots of those H2 valleys, so-called in France and in Europe. And so Europe reacted with a vision, detailed plan, and not that easy objective to tackle: net zero greenhouse by 2050. And we'll see on the next slides, transport segment by transport segment, the conclusion of that on the definition of that is not exactly the same, but very huge challenge to tackle by 2050. As a result, money. So Europe wants to help and to support all the industries, all value chain, to tackle this kind of challenge. So more than 100 billion euro expected for a 6-year period. So numbers are supposed to be officialized on next week's, and all the cluster 5 and so on will be clarifying all the projects. But not only the Europe, but also countries. France, 7.3 billion euro just for everything out of aviation, because aviation is managed by another plan. And Germany, 9 billion euro, and also the region. So lots of money on the table to help and support the industries to tackle this very, very challenging around hydrogen. So second reaction of the market on the value chain is all the stakeholders are trying to partner, because everybody comes to the same conclusion that won't be that easy, and cost and effectiveness are key. And one way to manage that is to gather and make some and build some kind of complementary partnership. So you have some logos, some names. Everything is public, just extracted from the web, and we have some cases involving Air Liquide and Toyota, Air Liquide and Siemens for electrolyzers. So Pierre, if you want to react 1 second of one or two of those partners, partnership which are concerning Air Liquide, if you want to add something.
Yeah, do you hear me correctly?
Yes.
Okay, yes, indeed. I mean, you know, we are producing hydrogen, so obviously electrolyzers will become one of our main assets in the future. So we teamed with Siemens, who is one of the world leader in making electrolyzers, and now we are talking about going several decades above what we did so far. I mean, so far we are talking about megawatt. Now we are going to talk about 100 watt or even gigawatt of electrolysis, and that's the reason why we made this partnership with Siemens. We have also partnership with Toyota. Because the Toyota is an end user and is also the historical user. Our CEO and the CEO of Toyota created, for example, the World Hydrogen Council in 2017, which is now gathering more than 80 large companies. And of course, well, we have many others partnership, and I will show a few examples in my presentation.
Okay. Thanks a lot, Pierre. So another example of what's happening on the ecosystem. So more on rail sector now, and we have Alstom, which are Siemens. We have partnership between Siemens and Ballard, which is providing the fuel cell. We have Alstom, who recently bought Helion, the fuel cell French fuel cell provider. We have Alstom and Snam. We are bringing on the Italian rail market a global offer, train plus molecule. So again, just to illustrate that things are moving, and lots of very interesting partnerships are now in place to optimize the value chain. Sustainable mobility. Very interesting diagram that has been published a couple of years ago. I think it was 2019. That's, I won't go into details, but that's made a strong differentiation between different kind of usages. Okay, separating the small cars, medium and large cars. So small cars, very interesting. Capgemini Engineering has having a very interesting experience on that. I think everybody is aware that we work with Stellantis on Amy. So this kind of car is interesting. The diesel engine has to probably be replaced on next years because of the CO2 rules that will be applicable to this kind of vehicle. So lots of different use cases, some a little bit strange, okay? Having city buses available in 2025. This is true. There are many cities in France where you have when you can meet and see some hydrogen buses. Okay, but these are experimentations. This is to us and to me not the real reflection on the market. This is just an experiment to test and see how things work, and notably not just from engineering perspective, but also from the TCO, from operator perspective. So interesting to see what's there, and notably here. Okay, they align naval and aviation, which is not going to happen this way, and we'll see that in a couple of seconds. Just to summarize, from an engineering perspective, our vision on how we can differentiate and separate the different use cases. Aviation, this is definitively the strongest engineering challenges because you have to face the high voltage, high power requests from going to 230 volts to something around 700 or maybe 800 volts. The power, which is to be very big, thermal challenges, cryogenic challenges, engines to be modified, safety, while there is another solution, which is synthetic fuel. And everybody knows, in fact, the difference vision between Airbus and Boeing. Airbus believes on both hydrogen and synthetic fuel, while Boeing just believes on and relies on synthetic fuel. Interesting to see what's happened there. The rail. I beg pardon towards any Alstom person who is attending this school, but I think that engineering challenges are moderate compared to aviation. Why? Because any diesel train is already an electrical train, and we'll go on some details in 1 or 2 minutes. Automotive, but this is valid for other transport means. The key is to target the captive fleet with high usage rates. Let's say if you have a personal car and if you are not using your car for 3 weeks, and if the car is just by itself on your parking, after 2 weeks, you don't have the same quantity of hydrogen into your tank because it leaks again. So for the cars, taxi, yes, but personal car, maybe not. But I think Pierre will come back later on that on the distribution challenges. But buses and trucks, as we'll see in 1 minute, there are huge challenges on CO2 emission for automotive sector. So the first reaction is electrifying, putting batteries. This is a great solution, but there are issues on autonomy first, and also the time to recharge. And definitively, hydrogen is the next step. We'll go on some details in 1 minute. And there are potential niche markets, as for example, mining trucks, agriculture, and some others. And naval is coming. Some kind of summary. The key is total cost of ownership. The cost to engineer, the cost to operate, and the cost and the price of the green hydrogen. If not using green hydrogen, definitely you are losing some CO2 credits, and this is not the objective. Present time is to experiment and test with massive subsidy support. But what for tomorrow, when China will enter, because there is no doubt China will come into the group. They have the capability to. They are using coal, sure, but they have huge opportunities to generate green hydrogen. So they will come. This is definitely for sure. The challenge is effectiveness, and success relies on H2 competencies, which are rare in the market. So this is why, for example, we are building some kind of training for our clients. Strong system and system engineering. to optimize the connection between the different bricks, and intensive use of simulations and taking the best of the digital factor. And there I want to talk about the digital twin that can tackle a lot of different use cases. So let's go rapidly onto details. For sure, the presentation will be available. On the rail section, there is a very interesting study which has been made by the French Parliament a couple of years ago. So there, the objective is for SNCF, the French operator, to eliminate by 2030 any diesel. Okay, so what we can see is everything that could be electrified has been electrified, as is in France. Okay, so what remains the intercity train and regional trains, and this is the market to be tackled in the rail market. And here you see lots of logos, all the value chain from fuel cell, auxiliaries, and all the OEMs dealing with the vehicles, the fleet operator that we don't have to put out of the loop, and the energy producers. And again, the market can be split onto different blocks: electrolyzer, supervision, which is key. I mentioned that it's a key to control the hybridization of the energy inside a car or a bus between battery and fuel cell. But it's the same when you produce energy. Okay, it's the same. The real-time supervision is something quite interesting, and also the energy provider, and possibly including nuclear. And so some logos there. This is not going to be exhaustive. So just to illustrate how the market is positioning. Okay, so after the rails, your automotive. So let me going fast because I'm conscious of the time. So there we have lots of details because the Europe has been very prescriptive and very detailed on kind of usage, and the ambition is great. Okay, reducing by 55% by 2030, being sure that the final target is addressed. And again, the same kind of ecosystems, the same kind of logos everywhere, because definitely for industrial stakeholder, objective is to cross-share and cross-feed between different industries. Okay, with some interesting positioning, like for Toyota, which is building cars and also building not the fuel cell, but the package around the fuel cell. So I was talking about the automotive and all the subsegments which are also interesting, agriculture and so on. So again, the same message is we have to cover the whole value chain to ensure performance, and notably economical performance. Oh, and there a very interesting example, but I won't go into details. I do advise you to go to the H2O subsidized project by Europe, which is having Air Liquide and Iveco and some very interesting stakeholders there, to work on the use case on distribution, integrating the logistics. Okay, there you have different use cases. You take into account not only the truck and not only the modularity between truck and other environments, but also the distribution, which is key. If you can go to the next slide. Okay, aviation. Again, it's the most challenging battlefield because of everything I said before, the cryogenics and so on. But also in an aircraft, we can use hydrogen not just to produce electricity, but also to be burned onto the engine. Okay, but there will be a cost effect. So can you go on the next slide? You have a very interesting study. I think most of you are aware about that. McKinsey published that 1 year ago. So very interesting messages to see that, okay, for 20 years or more than that, the aviation industry did its best to reduce CO2, definitively. But the contribution is not sufficient to go to achieve the 2050 challenges. And there are two very interesting projects run by Airbus at the moment, so-called POD, with the beautiful aircraft and the 6 propellers, where everything is embedded. So the fuel cell, the tank, the pipe, the compressor, the humidifier, so everything is embedded on a single box, which is under the wing, which simplifies the impact on the airframe. And another project very interesting, which is, okay, I'm having this very cold molecule, minus 253 degrees inside the aircraft. Can I use it? Can I use it to act on supraconductor level to ease the transmission of the electrical power? So kind of interesting projects are running by Airbus, run by Airbus at the moment. Okay, just 1 minute on that. So it's a kind of very detailed list of use cases, and again, that will be accessible after this webinar. To put on a paper from an engineer perspective, where are the challenges when talking about hydrogen in aviation? For example, as you know that the pilot is using the fuel to control his center of gravity. How is it possible to do that with liquid hydrogen when you have some bubbles stuff into the hydrogen? That will be quite challenging if we want to dump the hydrogen outside the aircraft. So very detailed use cases, very interesting use cases where engineering and the expertise on the system and the subsystem is key again. And also what's key is having experience on hydrogen within the Capgemini engineering, and notably in my R&I team. We have more than 40 PhDs. I'm not talking about engineers, really PhDs having a strong and niche expertise on hydrogen and all the subsystems. So this is key. This is key really to support our client to tackle this hydrogen challenge and all the complexity. Naval. So naval is quite very interesting because the range is so large. You have a project nowadays, running project in the form of experiment, as I said before, for the bus. So you have ferries in the northern countries where people are using this kind of transport, and there is a very affordable green electricity thanks to hydraulics. So you have ferries, okay, 400 kilowatts, but you have also plants for cargo carrying 23 megawatts fuel cell and 40 tons of gaseous hydrogen. I'm sure that Pierre will say that liquid would be best. And we have lots of variety. And you have this image on at the bottom. This is very small boats. We are quite proud of that because it's a boat where Capgemini Engineering will go to the race next 10 days from now by the Monaco Yacht Club. It's competition, okay, for academics mainly, and all the ecosystem to have a race on the electrical boats. And we will be there with the hydrogen boats powered by the 3 kilowatts fuel cell. So, and as written on the left part of the slide, so the challenges for naval is very interesting. Why? Because this is the single market where expectations is to have an increase of the CO2. Increase of the CO2 if nothing is done, while at the same time Europe is putting a lot of pressure. So definitively naval is a very interesting market to be tackled. This slide has been extracted from the study I was mentioning before, run by the French Parliament. And this is the vision of SNCF, so the French rail operator. What's interesting is that SNCF is considering what's happening on the left part of the image. Okay, taking care of biomethane, taking care about how the electricity is produced, because there is a clear vision that everything is connected. Everything is connected from the production to the distribution. That will be multimodal. Pierre, now it's up to you.
Okay, thank you, Jean-Luc, for this very interesting presentation. First of all, I'd like to thank Capgemini for inviting me to this webinar. By the way, I'm really impressed by the number of people who have registered. It seems like you are more than 300 people worldwide. I'm impressed but not surprised because I see the growing momentum and growing interest about hydrogen. And I'm going to discuss with you about what we are doing in my company. I'm not going to sell you dreams. I'm going to talk about real stuff and real industrial investment, which are now ongoing. So I am the head of innovation in a subsidiary of Air Liquide Group. So first I will tell you who we are, what are we doing there, because we are now one of the very few companies at the forefront of the hydrogen market. I will explain you some basics about what's going on this hydrogen mobility market from the gas company perspective. Then we will talk about technology, because of course technology is key for that. So technology mainly based on our business, which is to produce and distribute this molecule, but also we help our customer to store this molecule onto their mobile application. And I will conclude with a few examples of a very exciting application that nobody was talking about even less than 3 years ago. So first, who is Air Liquide? Actually, we are the world leader in industrial and medical gases. So we produce oxygen, nitrogen, we produce hydrogen, of course, and a bunch of other gases. It's a 21 billion euro company with 66,000 employees worldwide, and well, we have been very busy, you may imagine, during this COVID-19 crisis to produce a huge quantity of medical oxygen to hospital, and we have even produced 10,000 respirators in less than 50 days last year to serve the hospital. So, you know, hydrogen is a key issue, but also oxygen is a big one. And within Air Liquide, within the group, there is the high technology subsidiary, which is called Air Liquide Advanced Technology, which I belong to. And this is where we started doing hydrogen in Air Liquide. And we started that a long time ago, more than 60 years ago. We started to make some cryogenic tanks for storing liquid hydrogen and liquid oxygen aboard the future European rocket, the Ariane family. And thanks to that, in the 90s, we started to diversify ourselves on mobility with hydrogen, thanks to all the competencies we got from space. Then a few years later, we started to build up hydrogen refueling station, so gaseous station delivering hydrogen at high pressure between 350 bar up to 700 bars into fuel cells vehicle. And now we're talking about aerospace. We have been involved in aerospace, producing gases aboard the aircraft, mainly nitrogen and oxygen. So, given the fact that we are doing space with liquid hydrogen, we do aerospace, we do hydrogen energy and all that. We do also a lot of cryogenics. Obviously, we are now at the forefront of this new revolution, which is to use hydrogen whenever a mobile application needs it. So now, okay, as I said, starting from space, and you see now we are going to fly a demonstrator. This this small, maybe I can show my pointer here. Over here, this small demonstration aircraft has already flown with fuel cell and gaseous storages. Now we are going to retrofit this aircraft with liquid hydrogen to prove that, yes, indeed, we can safely operate liquid hydrogen aboard aircraft. Now, usually there are three main questions about hydrogen. Is it safe? Is it green? Is it cheap? So we are going to address all these questions. First of all, in terms of safety, we have been using a million tons of hydrogen per year since more than 60 years, as I said, not only for the Ariane rocket, but also we use hydrogen to desulfurize the petrol, for example. That's the reason why we have a huge network of more than almost 2,000 kilometers of pipeline. And you may imagine, in order to operate all those plants, 200 hydrogen production plant, all those 120 hydrogen refueling station, we have done a lot of assessment, test, and tool for assessing the safety. So at least on ground, hydrogen, I can say, has been routinely used for many industrial applications. Now, second question is it green? On that graph, you see how much CO2, how much kilogram of CO2 we release each time we produce 1 kilogram of hydrogen. On the right-hand side, you see over here, hold on. Okay, it's about 25 kilogram of CO2 released for each time you produce hydrogen with an electrolyzer, which is fed with non-green power, which is the case in many European countries, which are strongly relying on coal and gas. Now, in Air Liquide, what we do, we use natural gas. This is the way we produce industrially the hydrogen. And we do what we call the steam methane reforming. That means the natural gas is mainly methane, so CH4. So we break the CH4 molecule in two. We release the CO2 on the atmosphere, and we keep the hydrogen. By doing that, we release 11 kilogram of CO2 for each kilogram of hydrogen. And now, in France, we are doing something else. We are doing again electrolysis, but given the fact that our mix, energy mix in France is really strongly based on nuclear power, 75% of the electrical power in France is coming from nuclear plants, which we can consider as fully decarbonized. That means here we can drop down dramatically the impact of producing hydrogen because we use electrolyzer fed by nuclear energy. Another way, in the middle of the screen over here, would be to make the same reforming of natural gas, but instead of releasing the CO2 to the atmosphere, we can capture that CO2 and store it underground. There are huge reservoirs right now we are investigating. We can either put this CO2 back into the well where the original methane was extracted for, or better, we can put that into very deep aquifer, which has huge amount of water, salted water, between 1 kilometer and 2 kilometers below the ground surface. And the overall volume of CO2 that the geologists told us we could store is exceeding 10,000 billion tons. So that means with aquifer, we probably have more than 300 years of storage available, given the fact that today the humankind are releasing roughly 30 billion tons per year. Now, we can also draw the carbon and the hydrogen from biomass. In that case, when you put the biomass into a methanizer, you get a mixture of CO2 and methane. So we separate the CO2 and usually we release it to the atmosphere. It's not a problem because this CO2 was pumped out of the atmosphere by the plant. So we are just giving it back to the atmosphere, and the remaining biomethane could be reformed to produce biohydrogen. That's a way, and by doing that, the amount of net CO2 is very low. There are other ways. The ultimate one is on the left-hand side here. Again, we produce biomethane. We separate the CO2 from the methane, and we produce hydrogen from the methane. But instead of releasing this bio CO2, we capture it and store it underground. By doing that, we are just sucking out the CO2 out of the atmosphere. That means each time I produce 1 ton of hydrogen like that, I remove actually 5 tons of CO2 from the atmosphere. So you see, depending on the way we are going to produce the hydrogen, depending on the feedstock, depending on the green content of the primary energy, indeed, we can really decrease a lot the impact of the production of hydrogen. And that's the reason why my company has committed by 2035, we will have, despite the fact we expect at a minimum a 3-fold increase of our production of hydrogen, we will divide by 2 the amount of CO2 we release thanks to carbon capture, thanks to green electricity with electrolyzer. And at the end, by 2050, we target complete carbon neutrality, not only for hydrogen, but for all our gas production. And we are one of the very few companies which has committed in front of stock market to do that. So if we, and that means we will really do it, because now stock market will have no pity. I mean, if we do not meet our commitment, our shareholder won't be very happy. And last, most important, is the cost. The cost of producing green hydrogen. On that graph, you see the cost for producing 1 kilogram in US dollar. Last year, we were at about a little bit less than $6 per kilogram of hydrogen. I'm talking about really green hydrogen. And you see that price will drop sharply in the coming years. It's already doing that. Today we are more between $4 and $5 dollar per kilogram. And what is expected? We see the acceleration of the cost reduction, and we may end up with a cheaper hydrogen much sooner than expected. and we should be in the range of $2 to $3 per kilogram for green hydrogen. You see the bottom line over here is the cost of gray hydrogen. So when I just make the reforming of natural gas and I release the CO2 outside. Of course, this is the cheapest way to do that. It's just $1 per kilogram. But in 9 years from now, we will be in the range of $2 to $3 per kilogram of green hydrogen. And this is really important because you have to know when you replace a diesel engine by a fuel cell on a car, with 1 kilogram of hydrogen, you can drive 100 kilometers. And to drive 100 kilometers with gasoline or diesel, you need 5 kilogram or 6 liters of diesel. That means 1 kilo of hydrogen will replace 5 kilogram of diesel. So even if we are at $5 per kilogram of hydrogen, it's the same as 5 kilogram of diesel. For the aviation, it's even better because aviation will not show up before 2035. By that time, we expect to be in the range of €2 per kilogram. And on aviation, given the fact that the aircraft, once they are on their cruise mode, have a much better efficiency than a car in a city, we replace 3 to 4 kilograms of kerosene with 1 kilogram of hydrogen. So kerosene today is sold at around a little bit less than $1 per liter. And if the hydrogen is €2 per kilo, that means we are almost on par with kerosene, but with something which could be totally decarbonized. So that's really important. To do that, we need to sell a minimum volume of hydrogen. So that means we have to install about 65 gigawatt of electrolyzer. This will cost a $50 billion investment over the next 10 years. So this is something which is quite achievable by all the industrial gas companies which are on the market right now. So that's the reason why today hydrogen mobility markets are really emerging. With each day there is a new application that we didn't know. Initially, we thought that only individual cars would use hydrogen. The problem with those individual cars is that you need many hydrogen refueling stations. So today, each station is able to refuel 100 to 200 kilograms per day. That means something like 20 to 30 vehicle per day. That's small. I mean, on a highway, a large gas station can refuel 1,500 vehicles per day. But this is growing. What we are looking at now is really which is something which may emerge in the next 3 to 4 years, are large trucks. The advantage of large trucks is that they are captive fleet. You don't need to have a huge network of hydrogen refueling station. You have to put those stations along the main highways. These are hydrogen intensive consumption. Well, we are now working a lot with many truck makers to make this happen. In Norway now, they are talking about using hydrogen for ferries because, you know, in Norway, there are many fjords. A fjord is really narrow with a very high and steep cliffs. That means all the exhaust gases are trapped inside the beautiful fjord. So that's the reason why the Norwegians are keen at switching rapidly to hydrogen. And why in Norway? Because they have a lot of hydropower available, even also windmill power. That means they can produce massive amount of hydrogen, totally green, for their ferry. And they are now building the ships, and we are bidding to put the huge amount of liquid hydrogen on all the ports along Norway. Another application that we talk about a little bit is hydrogen for aviation. This popped up a few months ago with the announcement from Airbus. Actually, we have been working on that for more than 10 years, and I think now it's time to make scale 1 demonstration because really aviation is probably the only mobility which has no choice. You can always put a big battery on a truck or a small battery on a car, but I think you cannot put batteries on an aircraft because they are really too heavy. So there are different ways to transport the hydrogen. So we have a primary production of energy, as I said, either by electrolysis or steam methane reforming. And then we can either transport on liquid form or in gas supply with a bottle, pipeline, or truck. The Japanese are even now building up a new ship to transport a huge amount of liquid hydrogen from Australia to Japan. And the ship has been put on the water. And then on the right hand side, of course, you have to distribute. So either you distribute it liquid for trucks, for ferries, for aircraft, it will be liquid. For cars, it will remain gases, because the problem of liquid is it evaporates. So after a few days, your tank may be empty. So it's preferable to keep high pressure gas for individual cars. But for all other captive fleet, liquid hydrogen is definitely much better. And it's cheaper for us. I mean, if we have to transport a million tons of hydrogen in many points, what you see here, if your hydrogen refueling station, for example, is 400 kilometers away from your production plant, if you have to carry less than half a ton per day, it's still cheaper than doing to do that with 300 bar truck rather than liquid. But whenever you exceed 1 ton per day, the logistics with a gaseous truck will be tremendously expensive. So that's the reason why we are switching actually to liquid. So the liquid, a few words about liquid hydrogen. The interest of liquid is that today on a 200 bar truck, you have a 30-ton trucks carrying 300 kilograms of hydrogen. With liquid, with, I would say, a 15-ton truck, you transport up to 4 tons of hydrogen. So basically 10 times more. Of course, this hydrogen is at minus 253 Celsius at 1 bar, and still a very light liquid, 70 kilogram per cubic meter. Just remind you, water is more than 1,000 kilogram per cubic meter. Here on the left-hand side, you see hydrogen does not emit any visible flame when it burns. You can see here on the right, we are burning propane, so we see the flame, whereas on the left-hand side, we are burning hydrogen, and we don't see a flame. We can see the flame only through a screen, through an infrared camera. So that's also dangerous. We have to be careful. You don't see when hydrogen is burning. So, but keep in mind the main important point: hydrogen is 70 kilogram per cubic meter when it is liquid, and it has to be stored at minus 253 degrees. So, how do we do that? First, we have to liquefy the gas. This is really the core business of a liquid, to liquefy gas, and we do that always the same. We compress, we cool down through a heat exchanger that you can see on the right-hand side, and then we have a turbo expander, which is going to expand the gas, and this is where we produce the cold power. So that means we master very complex turbo machine. The small one here can rotate at more than 300,000 RPM. The larger one are about 20 to 30 centimeters in diameter, like a helicopter turbo engine, rotating smaller. So depending on the temperature, depending on the flow rate, we can adapt those turbines. So basic technology, the heat exchanger, the turbo machine, and also you have to put for hydrogen all that in a vacuum enclosure. Hydrogen is very cold, so you have to put that into a kind of thermos, DIWA, with vacuum. So vacuum, turbo machine, and heat exchanger are the three main technology. And also we need some catalyst, because hydrogen has some fancy characteristic, and we use catalyst to cope with that. And so I told you I'm not going to sell you dreams. We are doing it. I mean, you see on the left-hand side a huge, the biggest ever built hydrogen liquefier, production and liquefaction of hydrogen in Nevada. 30 tons per day, so 10,000 tons per year. We are now designing a 100-ton per day system, and we are even thinking about much larger hydrogen production system. And so we are going to invest. We have already invested the one you see here in Nevada. It was in 2018. Now we have recently invested in the largest ever built electrolyzer in Canada. Why Canada? Because they have an excess of hydraulic power, which is completely green. And so with 20 megawatt, we can produce several 100 tons of hydrogen per year, totally green. And this is climbing up. That's the reason why I was talking about this teaming with a various company like Siemens for those electrolyzers, because you see a range of classical electrolyzer in 2018 was 1 megawatt. 2 years later, it's 20 times, and in the next 2 years, we have to make again a 5-fold increase. So this is ongoing, and it is based on what we did for large science. In science, they use a lot of liquid helium to cool down superconductive magnet, whatever it is at CERN, on ITER, and those helium liquefier are working at even colder temperature, but we have reduced completely the same technology. So I can say that thanks to large science, now hydrogen can really emerge as the energy market. Then we have to distribute. So this is a type of truck trailer. We do that. We build our own trailer. We can store between 3 and 4 tons on those trailers. There is a boil off because those are vacuum insulated containers. But despite the fact it's well insulated, there are still some boil off. The hydrogen is permanently boiling off, so we have to recondense it. And we have some losses today. But you have to know, up to now, we didn't care that much about those losses because the liquid hydrogen market was very small. It was mainly for rockets. Now we are talking about million tons of liquid hydrogen per year. No way to lose any single % of hydrogen. So we are now closing completely the logistics chain to avoid any leakage. By the way, hydrogen is not a greenhouse gas because it's a small molecule with only 2 atoms, and you need to have at minimum 3 atoms to absorb the infrared and be categorized as a greenhouse gas. So even if we have some leakage, we will not create any additional greenhouse gas with hydrogen. The storage, very important. So there are 2 types of storage. The basic one for industry. Here you see what we have installed in Kourou, in the European spaceport in French Guiana in South America, where we have very large trucks to refuel the launch pad of this rocket here. On this rocket, we have 21 tons of liquid hydrogen, that will be burnt in less than 10 minutes by the Vulcan engine over here. So actually we have built a kind of huge refueling station to refuel the hydrogen, which is the tank over there, and also the oxygen over here. And then the outlet of the engine, we just produce water. And we have done more than 700 tanks like that on the 56 flight without any problem. So that tells you that we can master really safely those huge tanks. We have to master, of course, the fluid which is inside. Here are a couple of examples of tanks. We have flown those tanks in space on satellites, not only rocket, but on satellite. The problem of satellite, the hydrogen or the helium, in that case it was helium, is under microgravity. So you see inside the tank over here, when the engine is on, the tank, the hydrogen is settled at the bottom of the tank due to the acceleration. And as soon as you switch off the engine, you are in microgravity, and then the hydrogen is distributed all over the tank. So we are able to master all that as well. So we did some development for automotive industry, for also as I said, for demonstrating the usage of hydrogen aboard aircraft, because Airbus is now getting really serious. These are the three model that Airbus is thinking about. You have to know that with Airbus, they will target probably at the beginning what we call medium-range aircraft, which still represent something like a quarter of the CO2 emission of the entire aviation. So the other aircraft could be made completely environmental friendly. For the larger one, we may better use the e-fuel based on CO2 captured, green hydrogen, and with CO2 and green hydrogen, we can synthesize the kerosene. And by doing that, since we have captured the kerosene, the CO2, we can reduce the CO2 emission of the aviation by 50%. And in terms of distribution over airport, we're talking about distributing something like 5 to 10 million tons of hydrogen by 2050. There will be something like 10,000 aircraft. It's not a big deal for us. I mean, we're talking about a few thousand trucks, mobile trucks, to refuel the aircraft. So we think that the infrastructure for airports is largely affordable. And the last big and new application is for ships. Actually, we have been working on ship for years with cryogenics to recondensate the boil off of large LNG ship carriers. But now we see big projects popping up, real big investment in Norway. So we are participating to that. So you see, it was just to give you a broad outlook of what's going on. So we started from space, a very high-end application. Thanks to the technologies and the competencies we have developed, we are now able to decrease the cost of the hydrogen, to make the liquid widely available, because anyway, we need it for our own needs for the logistics, and then this liquid will become a kind of commodity in the coming years, then serving many applications from ships, trucks, train, and aircraft. So this is a promising future. What is funny is that we started from space with hydrogen, and now space, especially in US, is coming back to kerosene. I mean, the SpaceX rocket is a kerosene oxygen rocket, and the next one from SpaceX will be an LNG powered rocket. So it's funny that we go on one way for ground mobility and the other way around for space. But in Europe, our Ariane 6 rocket will still use liquid hydrogen. Okay, so I think hope you have enjoyed my presentation, and both, I guess, Jean-Luc and I would be available for replying to any question you may have.
Thanks a lot, Mr. Crispy. Thank you, Mr. Chaboudi, for the insights and for taking us through the industry's rendezvous with hydrogen. So that's right that the timing is already over, so we have lots of questions. So what I propose maybe it's to answer one or two questions, and of course we will answer later to the ones that we wanted to answer. So maybe one first question. According to you, so what would be the main challenge about hydrogen in terms of mobility?
Okay, there are many challenges, of course. We're talking about new fuel. So the main one, and maybe surprising you, before making green hydrogen, we have to make gray matter. We need competencies. Because liquid hydrogen, as I told you, was so far a kind of confidential activity with a couple of launchers worldwide. Now, this confidential activity is going to grow exponentially. So the first challenge is to get the manpower and the expertise. That's the reason why many people are trained right now. But we need, I mean, today we are talking about a few hundred, handful of people worldwide. We are going to talk about several thousand people in the coming years. So that could be one of the challenge. But then after that, first of all, as I told you, of course, safety is the key issue, whatever it is for a truck, a ship, or an aircraft. But we do not say that safety will be more complex with hydrogen than it was with kerosene on aircraft. It's a different fuel which will pose different challenges, but not really much more complex. For example, the US Air Force has done a lot of tests on liquid hydrogen. They fired a bullet on liquid hydrogen tank. They could never ignite the liquid hydrogen, and they even concluded that it's probably, it is their word, it's probably easier to ignite jet engine fuel than liquid hydrogen. So, but at the end, the problem is not just safety, because it's always possible to make something safe. The problem is that we want something safe and competitive. If your aircraft has to be extremely heavy to make it safe, it's not a good one. So the challenge, I would say, is safety versus competitiveness. And the last one, all that is bullshit if we do not have the green power upstream. So at Air Liquide, we are trying to do our job from production to distribution as green as possible. But if we do not get the low carbon power upstream, then we will be out. But I think now the energy company are really tackling this issue.
Thank you, Mr. Crespi. So maybe we can have as well the point of view of Mr. Chabaudy from Capgemini Engineering, and maybe I combine the second question for you, Jean-Luc. And what about as well the way that Capgemini Engineering can also accompany this kind of challenges and issues? Jean-Luc, I think you must unmute.
Okay, yeah, I am. Yeah, thanks for
Thank you.
this question. So the challenges from an engineering point of view, the question is the TCO. As I said before, nowadays Europe and countries are putting money on the table to lots of subsidies because it is absolutely necessary for the industry to invest on more challenges. But the TCO is key. At any stage, if you can say this hydrogen value chain is a rocket, at any stage of the rocket, you have the cost. So Pierre detailed lots what's the cost issues on different techniques to build and produce hydrogen, eventually to transport hydrogen. But there are other layers, okay, for the company, for the vehicle OEMs to redesign or eventually retrofit their vehicles. Engineering is key, and notably because those industries normally, as Pierre was saying just before, are not used to manipulate this strange molecule, this strange product, okay, that leaks and that's inflammable and so on. So reducing the cost at any stage of the rockets by having a strong expertise on the system by itself and how this system is connected to the other ones. For example, if I'm discussing with a fuel cell provider is providing fuel cells, but no client is asking Plug Power or Ballard or Symbio or Helion before, just the fuel cell. The clients are asking for the system, which is the fuel cell, the compressor, and all the accessories around. And so having some engineering capabilities there to help the customer to build the system at any stage around the fuel cell, integrating the hydrogen system onto the vehicle, operating the vehicle, and operating the fleet of vehicle in connection with the hydrogen distribution. So that requires a huge system expertise on any stage. And as I said before, that needs to do that, you have to have system engineering experience on any level, okay? And I think that Capgemini has this kind of expertise. We have to have a strong experience on the engineering disciplines, electrical distribution, safety, cryogenics, thermal management, and so on. And I do think that Capgemini has a strong record on that. And we have to have HO experts. As Pierre was saying, he's absolutely right. They are just rare in the market. So we decided, thanks to RNI, so the organization I'm working in, to recruit PhDs, not consultant, not engineer, PhDs. Those people having a very, very narrow expertise, but very in-depth expertise. And we can see that they bring kind of very interesting value to support our client, because you need to have this hydrogen expertise. And after that, as I said before, the digital simulation is key for me, for us. You have to use simulation and digital twins to anticipate and predict any kind of use cases. That was the intent of the slide with all the subsystems onto the aviation. So you have to identify the key challenge for an energy provider, for a fleet operator, for an OEM manufacturer, for a fuel cell provider. So you have to tackle the use cases. And I do believe, and we do believe, that digital twin is a very interesting way to bring value.
Perfect. Thank you so much, Jean-Luc, for this intervention. And I particularly thank as well Mr. Crespi. It was a real pleasure to get you on board with us for the huge preparation for this intervention. Thank you so much. That
Thank
was
you for inviting me.
really helpful, really qualitative, and with added
And
value.
just
Thank you so much.
a last question, maybe. We did not prepare that, so I'm sorry for that. But I think that it could be interesting to add eventually some documents out of the pure webinar. I'm pretty sure that Pierre is having some interesting document to share, and we do, and not only the study that we published a couple of months ago. I have the name in front of me, the 55 tech questions to accelerate EU recovery and pave the way to climate neutrality. I think it's a very interesting document. I was mentioning McKinsey study earlier on, but I think this document is quite interesting, and I think it will be quite interesting for our audience to have access to this document.
For sure, for sure. Yeah, good point, Jean-Luc. Perfect. So thanks again. Thank Mr. Crespi, thank Mr. Chabudi for your time. Thanks a lot. And thanks to the audience as well for attending today's webinar. And of course, if you have other questions or discussions to go further, please contact us at our email marketing address. We will have a pleasure, of course, to discuss with you and to answer your questions. Thanks to you, and on behalf of Capgemini Engineering and Air Liquide, thank you for joining us today.
All right.
Thank you. Bye-bye.